the average power to be precise. So I'll pause here so I can let my dog out. Alright, since this video will be a bit chaotic, since my dog keeps interrupting me, something that you know is like, I mean, like, I guess you know that I live with my family, and but at least one member of them will look over my dog, you know. It's not even my dog, it's our dog. But yeah, they are gone like to some people, to a friend's house, and I'm only me and the dog at home right now. And she is quite high maintenance, to be honest. But anyway, it's not really important. So sorry about that. So if like when she's making sounds, or she's making me pause the video, like bothering you in any way, it won't be like that. Like probably the next video she won't be here. You won't hear her. So yeah, let's keep going now. Alright, so we already went over the basics of AC circuits. Now the next part of the basics is basically how to calculate the power. And here we have a couple of examples, and this will be quite quick actually, because there are multiple ways of calculating power. I mean, like, remove the calculator from the piece of paper. Okay, so here what we have: find the average power dissipated in a circuit whose input current and voltage are the following: 10 volts peak, no, 10 amps peak at the sine of 40 degrees, and 20 volts peak at the sine of 40 degrees. So they are both 40, so we know this is actually a resistor. Alright, so it's not really like making a big difference, just like for us to know that. Alright, so one way to find it is basically just applying this formula here. PAV is equal with Vm times Im, which is the peak voltage peak current, divided by 2 multiplied by the angle, cos angle. So we can literally write this down. So PAV is equal with Vm Im divided by 2, which it will be equal with 20 times 10 divided by 2, and that one will be equal with 100 watts. And you may wonder, like, Alex, you did not use the cosine. Well, of course I did not use the cosine, because there is literally no difference in power. Like, no difference in the angle. Like, if I do 40 minus 40, that will give me 0, which is basically useless, isn't it? Because there is no difference in it. Because cosine of 0, if I think I remember right, that will give you 1, doesn't it? Let's check actually. Cosine of 0, yeah, it basically gives you 1. So it literally makes no difference. We can also like calculate the average power in like more normal ways, like using RMS if you want. You can like calculate the resistance first. That would be Vm divided by Im. That would be equal with 20 divided by 10, and that would be equal with 2 ohms. And then P would be equal with voltage square RMS divided by the resistance, and then that one will be equal to 0.707 times 20, all of it squared, divided by 2, and that one will be equal with 100 watts. Or you can do the other way around, like P is equal with the current, this time RMS squared, and therefore R is equal with PAV, it's equal with 0.707 times 10, all of it squared, times 2, which is the resistance, that will be equal with 100 watts. So yeah, there are like multiple ways to calculate it really. You are not limited to the normal one, but I'll suggest you do the normal one. Don't try to like do the RMS. I mean, if you want to try to do so, you can do it. But again, it's just simple to stick to the normal one, which requires the peak voltage and peak current. I guess these ones are good if you don't know the current, which is in this case, or if you don't know the voltage, which is in this case here. But anyway, let's keep going. Now, Example number 2 is determine the average power delivered to the circuit having the following inputs: voltage and current. And in this case, voltage is 106 peak voltage at plus 40, and the current is 40 sine at plus 70. And what's different from this compared to the others? Well, of course, the big difference is the angle. They don't have the same angle anymore. That means they are not really a resistor, so you can't really omit the cosine, because the cosine won't be equal to 1, it will be equal with a different value. Alright, so let's do it then. So Vm will be equal with 160 volts, and the angle of the voltage will be equal to 40. Im, it's equal with 40 amps, and the angle it's equal with 70. And of course we are going to use this formula that I told you earlier about angle difference to find the angle that we are going to use inside the cosine. So because we know these two value, let's apply that angle difference. Therefore angle difference will be equal with the angle of V minus the angle of I. There you go, which is equal with 40 degrees minus 70 degrees. That one is equal with minus 30 degrees. And because it's between these two lines, that one will simply be equal to 30 degrees, because it will give the opposite sign, which is instead of a minus, it will become a plus, so that will be simply 30 degrees. Alright, now that we know the cosine, we can apply the power formula. You know, Vm times Im divided by 2 times cosine of the angle. So therefore PAV will be equal with Vm Im divided by 2 cosine the angle, which is, let's actually write it, and therefore that would be 160 times 40 divided by 2 times cosine of 30 degrees, and that one will be equal with 2.77 k watts. So that is the power inside this first circuit really. Now let's calculate for the second one, and I expect you can see that you expect the second one to be actually higher, but it's actually lower, because yeah, this is 160 times 40, this is only 270 times 30, so yeah, it will of course be lower. But anyway, B. So let's write the values. So in the voltage, Vm will be equal with 270 volts peak, and it's got an angle of minus 70. So Vm is equal with 270 volts, and the angle of Vm is equal with minus 70 degrees. Im, it's equal with the peak value is 3 amps, and the angle is minus 50. So the angle in I is equal with minus 50 degrees. We apply the same formula to find the angle difference. So angle V minus angle I, it's equal with minus 70 degrees minus 50 degrees, which is equal with minus 120, isn't it? Let me wait. Oh, it's a minus, so that's already minus, that becomes a plus, yeah, and that one becomes just 20 degrees. And because it's minus 20 degrees again, then it's because between the brackets, then that one will be simply become 20 degrees. These are not really brackets, they are lines, they are just straight lines. And again, it just indicate the opposite sign. Now you can just calculate the power average, which is basically Vm multiplied by Im divided by 2 times cosine of the angle difference. Therefore PAV will be equal with 270 times 3 divided by 2 cosine of 20 degrees, and that one it will be equal with only 380 watts. A really big difference, isn't it? From the 2.77k down to 380 watts. Well, that's it really. So I mean, it's not it for the lecture. I mean, if you want, you can stop here. Now we are going to go to the last part of the lecture, Wait, can I call these lectures? No, it's a tutorial. It's more of a tutorial. Even if I can call them that, of the lessons, I guess I can call them. Anyway, I'm just going off tangent here. And the next part will be, actually I'll pause and I'll like get everything ready for it, and also drink some water for my voice. So I'll be back in a few seconds. Alright, so welcome to the last part of this lesson. And this last part will be about advanced AC circuits, brackets for this lesson obviously, because I mean I can't really call any of them advanced yet. We are not to the core of AC, but for you, for this lesson right now, you'll think that this is advanced, and you may wonder, and you may say, well, it's advanced because we are using multiple components. At the beginning, until now, we used only one component. Now we are going to use three components, and this is still very simple as well. Actually, it's not very complex because you use the same type of component, so it don't really mess up too much with the phase. There won't be too much of a phase difference between them. So yeah, first we'll start with this one, which all of them are capacitors. You have a capacitor in parallel with another two capacitors that are in series, and we are going to combine everything that we learned until now in this circuit here. And don't worry, after this capacitor circuit there is also an inductor circuit that we are going to work on. Alright, so let's get started. First we need to find the currents, IT, which is the total current, I1 and I2. I1 is this current going through here, and I2 is this current going through here. IT is obviously going through here to supply both of them, and they like split at this node. And you may go like, okay, so how do we start this? How do you calculate the current split inside capacitors, because they're not really resistors, you know? And now we can see the true value of reductance really, because now that we have do AC circuits, we actually found a way to transform capacitors into resistors, and capacitors inductors into resistors. Alright, so let's get started. I'll show you two methods to calculate the current in this problem, since current will be probably the biggest issue for you. So method one, we will use the total capacitance. So this 2 micro, this 5 micro, that's 10 micro. So let's see, C2 and 3, they are connected in series. So let's calculate these two that are connected in series first, which will be equal with 1 over 2 plus 1 over 5 micro, and that one will give us 1.43 microfarads. These two capacitors combined together will give us 1.43 microfarads. And then therefore the total capacitance CT are these two calculated in parallel as well. And because they are calculated in parallel, we'll just simply add them together. We'll simply do 10 plus 1.43, and that one will give us 11.43 microfarads. And there we have it. We have the total capacitance. We simplify this circuit into one single capacitor, and you can already see where I'm going with this, because now we can simply calculate it like a normal simple AC circuit. We can calculate the XCT value, like the total CT value, and that will be equal with 1 over 377 times 11.43 micro, and that one will give us resistance of 223 ohms. And there you go, we have the resistance. So now that we have a resistance, we can easily calculate the IT value, which will be 50 divided by 232, and that value will be equal to 0.22 amps. And there you go, we found the IT value as being 0.22 amps. So 0.22 amps are going through. Now we just need to find the value of I1 and I2. So to find these values, we need to find the resistance inside these two capacitors in parallel. So XC1, the X capacitor 1 resistance will be equal with 1 over 377 multiplied to its own capacitance, which is 10 microfarads, and that one will be equal with 265.25 ohms. And then we need to do it for the C2 in series with C3, which we already know it's 1.43, so that will be simply be 1 over, it's equal to 1 over 377 times 1.43 micro, and that one will simply be equal with, wow, it's quite a big number, 1855 ohms resistance. It's a ridiculous amount of resistance, isn't it? But anyway, it will work out. So now we know both resistances. We know this has got 265.25 ohm resistance. So let's write it here actually. 265.25 ohms. And this one here has got 1855 ohms. Now we can apply like resistance formulas that we know. Like one of my favorites, which is basically drawing this small circuit here. That has got one value at the top, 265.25, and one value at the bottom, 1855, and coming in is a current 0.22, and it will be 0.22 times 1855 over 2120.25, which is the resistance added together, and that one will be equal to 0.19. If you're wondering from where I get these values, well, that means you didn't watch my previous videos. I have an entire playlist on how to calculate resistors, and I'm not going to, each time I'm doing a calculation, I'm not going to like go and explain how to do that calculation if I've already made a video about it. So yeah, if you want to like know how to do the basics before going to this advanced AC stuff, then you need to like watch the previous videos as well. So that will be the current 0.19 amps, that will be I1. And I2 will obviously be the difference of it, so it'll be 0.22 minus 0.19, which is equal with 0.03 amps, and that one will be through I2. So now we found I1 and I2, so this one will be 0.19 amps, and this one will be 0.03 amps. Alright, so we already did two of them, and we already found the hardest components, which were the currents. However, there is also another method to do so, because you may say, well, Alex, yes, this first method is good, but it only works because all of the values are capacitors. What if I have different components inside of it? Well, then you can use method number 2. Okay, I'll let my voice relax for a second. That will be XC1. You will start with calculating the value of reactance, and we are going to use the angular velocity multiplied by the capacitance one, and we are going to first change all of them into resistors in a resistor equivalent. 265.25, they are the same values. If you're wondering, XC2 it will be different because it will be 1 over WC2, that will be 1 over 377 times 2 micro. That will be equal with 1326.25 ohms. And there you go, we got the resistance for XC2, and now we need the resistance for XC3. So XC3 will be equal with 1 over W angular velocity multiplied by C3, which will be equal with 1 over 377 times 5 micro. That's equal with 530.5 ohms. And you may wonder, like, well, Alex, how do you calculate now? Well, we made all of them into resistors. So basically the new circuit that we just created is this now, which is full of resistors. You know, we got X1, we got X2 and X3. And you may wonder, like, okay, so how do you calculate them? Because in a capacitor, you apply this format to add the two capacitors together in series. Well, because we exchange them into resistors, we can actually just add them together. So we can simply do XC2 plus XC3 in parallel with XC1, because this resistor is in parallel with these two resistors. You can already see how this method is very different from the first one, because now that we exchange all of them into resistors, we are using resistor basics to calculate it. And you may be curious, like, well, does it give you the same value? And I'm going to show you that it does. So 26.25 plus 530.5 parallel with 265.25, and if you do that into a calculator, you get 856.75 parallel with 265.25, and if you put that to a calculator, you get 232.1 ohms, and it's the same value as this one. This one is rounded down while this one is rounded up. It's a small difference between them, because you know there will always be a small difference between them, but you need to understand that both methods, they give you the same answer. They give you the same resistance, so it will also give you the same current, therefore. And it's quite impressive, isn't it? The fact that you can change capacitors or even inductors, if you want, into resistors, and by changing them into resistors, you can easily calculate their values and find their total resistance, or you can find their like currents going through them or anything like that. Simply getting all of their complicated components, all of the complicated things that comes with capacitors and inductors, and replace them with simple resistors. But yeah, so it's a good trick to know. Now let's go to the next part, which is like, what is the voltage in C1, C2, and C3 after 5 milliseconds, and what is the current in C1, C2, C3 after 5 milliseconds? Okay, so to calculate those, I have a separate page here with the answers for the calculations. So let's go through C now. Let me go to this new blank page, and now we need to calculate the voltage. So CV1, the voltage side C1 will be XC1 multiplied by the current 1. And as you know, the resistance inside the capacitor is 265.25 multiplied by the current 1.19, which is equal to 50.4. But it's supposed to be 50 volts, so we just round it down, because as you can see, they are connected. I can show you like on the resistor one or like on this one, but they are connected in parallel, so they should have the same voltage. However, for CV1 and CV2, no, for CV2 and CV3, they will have a different voltage. Actually, let me rewrite this one as well. So by rewriting it, I mean like I'm going to rewrite this part here, because it's there you go, it's 50 sine 377 times t plus 50 degrees, so we need to remember the 50 degrees in it. So CV1, it's equal with 50 sine 377 times t plus 50 degrees. Soon we replace t with 5 milliseconds as the problem asks us. Now we're just going to calculate for the other two. So CV2 is equal with XC2 multiplied by I2, and that one is equal with 1326.25 times 0.03 amps, and that one will be equal with 35.8, and that will be sine 377 times t plus 50 degrees. And this one CV3 is equal to XC3 times I3, and no, I2, sorry, there's no I3, there's no current, it's I2, because the same current goes through both of them and the current stays constant, only the voltage changes. And then that one will be equal with 530.5 times 0.03, and that one will be equal with 6, I think it's 6, no, it's 15.9 sine 377 times t plus 50 degrees. The degrees doesn't change yet. We are going to change it eventually, but not yet. Okay, because in voltage, the degrees, the angle stays the same. When we change it, well, we change it with inside the current. So voltage angle stays the same. Current angle is the one that's affected by the fact that it's a capacitor or it's an inductor. All right. So what I did is I rounded them down to like 35 and 15 volts instead of 8.9 because and 0.8 and 0.9 because these two are just too big, and I'll round both of them down because it needs to give me a total of 15 volts. And you can see like why it's important to be accurate with numbers, because 0.03 is not really the number that I got, and 0.19 is not not the number that I got either. And because I rounded them up quite a lot, because you're like 0.5, it really messed up this one here and also messed it up this one here. So that's why I'm rounding them down. But don't worry, you still get the correct answer if you round them down. It's important to make sure they don't go over the limit of 50 volts, because that will be the maximum voltage possible, because that's the peak voltage from here from the source. Okay, so now let's do the calculation. So CV1 will be equal with 50 times sine 377 times 5 milliseconds plus 50. Again, the angle stays the same. That will give us 39.34 volts. So after 5 milliseconds, there will be 39.34 volts through the first capacitor, through C1, which is this one here, C1. Now let's do it for, actually let's put it here so you can actually see the circuit while I'm working on it. So now let's do CV2. Again, it's like 35 times sine 377 times 5 ms plus 50. That one will be equal with 27.54 volts. Now let's do CV2, no, CV3. The second capacitor, there will be after 5 milliseconds there will be 27.54 inside of it. Now to the third one, after 5 milliseconds, to be equal with 15 times sine of 377 times 5 milliseconds plus 50, and that will be 11.8 volts. And if you add those two together, you will get 39.34 volts, surprisingly enough. So you know the answer is correct because those two values matches together, and they are supposed to match together because they are parallel from each other. And you also know that the source is equal with 39.34 volts at the same time, because all of them are in parallel to each other, so all of them need to have the same voltage when combined, when combined here. Alright, now the next one is to like find the current value after 5 milliseconds, and you may say like, well, isn't it the same value? And the answer is no, it's not the same value, because these are still capacitors. And again, because they are capacitors, then IC leads by VC by 90 degrees, so it will be plus 90 degrees to it. Alright, so then part D, CI1, it's equal with, we already know the current, which was 0.19 for C1 for I1, which is this current here. So that will be simply be multiplied by sine of 377 times 5 milliseconds plus 50 degrees plus 90 degrees, because they are capacitors, and in capacitors the current is leading by 90 degrees. And if you calculate that, that will give you 0.117 amps. Now for CI2 and 3, this actually let's just put I2, because it's going through, like both of them is going through the capacitor 2 and capacitor 3 I2. So that one, you know, it's equal with 0.03 amps multiplied by sine, and again we repeat the same one, 377 times 5 milliseconds plus that will be 140 together, and then the answer will be 0.019 amps. And can we check if our calculation is correct? Well, yes, if we add those two together we get 0.136, and now we can also calculate what the total current will be at that period of time. So we know that total current is 0.22, so we can do 0.22 sine 377 times 5 milliseconds plus 140 degrees, and that one will be equal with 0.135 amps. And it's, no, sorry, 0.136 amps. And it's got the same current, you know, when you combine I2 and I1 and I2, you get 0.136 amps, and when you do the same calculation for the IT, you get 0.136 amps as well. So the calculations are correct as well. If these two values were different, then one of the calculations are wrong. Like maybe you use the minus value instead of the positive value for them, or anything like that, you know. But anyway, I will again pause the video here. I need to let my voice relax for a minute or two, and then we are going to go to the very last exercise for this lesson, or lessons. I think I'll split this one in two because I think it's 2 hours long, and then that's it really. All right, so I'll pause here. Okay, so this is the very last exercise. Yay. Okay, not kidding. Actually, I'm not kidding. I'm happy as well to like finish with this one, and I don't know if I should be happy or sad, because you imagine, like, no, next video will be about polarities and complex, no, not polarities, about complex numbers, and that would be pretty easy. But after that one we are going to go into even more complex circuits, AC circuits, and yeah, I don't know how I feel about that. But since it will take me a while to like learn and understand even more advanced like series and parallel AC circuits, like proper series and parallel, not just like these ones that use the same components. But anyway, so let's go to the next one, which is this one. Here it's like a 50 sine, so 50 volts peak, and it's got a plus 70 degrees angle. And instead of capacitors, as you can see, we have inductors. And this one should go faster because I'll not show you the both methods, I will only show you one method. And the method that I'll use is the one that I change all the inductors into... Oh no, my battery is going down. Okay, you will see my head figure and you'll see it in the shadow. So let's go through it quickly before my phone dies. Okay, so that will be into inductors. So we will change them into resistors, and we will apply that method that you change all inductors into resistors or all capacitors into resistors. So let's get started. First, we need to find the same things. We need to find the current, the current 1, current 2, and we also need to find the voltage in them after 5 seconds, and the voltage inside of them after and the current inside, and the currents after 5 seconds. All right, so let's get started. So XL will be equal with WL, W multiplied by L. Therefore, XL1 will be equal with 377 times 20 millihertz, and that one will be equal to 7.54 ohms. XL2 will be equal with 377 times 5 millihertz, and that one will be equal with 1.885 ohms. And XL3 is equal with 377 multiplied by 10 millihertz, that will be equal with 3.77 ohms, quite low resistances. Okay, now let's calculate the total one, which is XL2 plus XL3 parallel with XL1. Therefore 1.885 plus 3.37, is it? Yeah, it's 3.77 in parallel with 7.54, and that will be equal with 3.23 ohms. So that is the total resistance, is 3.23 ohms, Now we can easily find the total current by doing the peak voltage 50 divided by the total resistance 3.23, and that will give us 15.48 amps. So that is the total ampage. Now let's calculate the for I1 and I2. So we split it. We have in one side 5.655, the combination between XL2 and XL1, XL2 and XL3, and then XL1, which is 7.54, and inside they are going 15.48. So 15.48 multiplied by 5.655 divided by the two values added together, that will be 13.195. It will be equal with 6.63 amps. That will be I1. And then I2 will be equal with 8.85 amps I2, because you do 3.63 minus 15.48, that'll give you 8.58. All right, so that's for B as well. We find the currents. Now let's write them nicely with the proper angles. So that'll be 6.63 sine of 377t plus 70 degrees minus 90 degrees. Again, because of the rules, inside an inductor lags by 90 degrees compared to the voltage, so it will be less by 90 degrees. So minus 90 degrees. I2 is equal with 8.85 sine 377t plus 70 degrees minus 90 degrees. And we are going to use these two values later for like when we try to find the current going through the inductors. Alright, now let's find the voltage. So C X, okay, there you go, XL I1 is equal with 6.63 yeah, 6.63. I need to slow down, concentrate. Amps, that's the sine 377 times the time, which is 5 milliseconds, isn't it? No, it's seconds. 5 seconds plus 70 degrees minus 90 degrees, and that will give me 6.01. So that is the current to the first one. Now let's calculate the current to the second one. So XLI2 is equal with 8.85 times sine of 377 times 5. Oh, I calculated the currents before. Okay, this is the now. These are the currents. The voltages are basically the same. To calculate minus 20 degrees, that will give me 8.02. We combine them together, we get 14.03. Now let's calculate the total current. So XLIT, which is equal to 15.48 multiplied by sine of 377 times 5 minus 20 degrees, and that one will be equal to 14.03. So it's correct because they match. Let's go to another page. Now let's calculate the voltages. Alright, so, oh my god, I'm doing this so fast. Again, it doesn't need much of an explanation. It's just a bit different because of the component, because instead of being plus 90 degrees on the current, it's becoming minus 90 degrees on the current calculation. And also yeah, and also the resistance is very different compared to the capacitor. It's good practice, and I want to show to you how to do when it's an inductor, in case you're curious if there's many differences between a capacitor circuit and an inductor circuit. Alright, there's no time to waste. So XL1 V1 it's equal with, and now we use the 50 sine 377 times 5 plus 70, because again in the first one, in the first inductor, it will be equal with the same voltage. That will be equal with 21.13 volts after 5 seconds. XLV2 now in the second inductor will be equal with XL2 times I2, and that one is equal with 16.7 times sine of 377 multiplied by 5 plus 70, it's equal to 7.06. Again, like, the angle doesn't change, it doesn't have any pluses or minus 90s, because the angle in the voltage stays the same, only the one in the current changes. XLV3 will be equal with XL3 times I2, that one will be equal with 33.36 times sine of 377 times 55 seconds plus 70, that's equal with 14.1, and then if we add them together, there's a small difference between them. This one will be 21.16 while this one is 21.13. It's not that much of a difference, so we can like say that yes, it's still correct. Okay, because I either rounded them up or I rounded them down. So this is how you calculate a circuit with inductors, and this will conclude this topic, which is the basics of AC circuits and how to calculate different components in them. I'm very happy that people are watching my videos, to be honest, and I hope you find them useful. It's quite late in the night now. I was hoping that my flash won't die so you won't see the shadow of my head in the video. But yeah, so let's quickly go over what we did today. Today we learned how to calculate the resistance, peak voltage, peak current inside an AC circuit that has a resistor inside of it, that has an inductor inside of it, and that has a capacitor inside of it. We also learned the phase difference between current and voltage when inside an inductor, and the difference between current and voltage inside the capacitor. And we also learned how to calculate the average power and how to calculate the angle difference between them. Alright, with this special formula here. And we didn't really use the power factor because this one to maybe be in a later topic. It is not really that useful for now. I don't even know why I put it in. I guess I put it in so that you can see it, because it was in the book, but I didn't really find much use to it anyway. And then we ended the lesson today by doing a bit of a more advanced circuit that has more than one element to it, like more than one inductor, like 3 inductors or 3 capacitors. And we did the calculations on them by finding their total current, by finding their current I1 and I2, and by finding their voltage and current at certain times, which is like 5 seconds or 5 milliseconds or anytime you wish, really. Okay, so that was the recap of what we did in these 2 videos, in these 2-part videos. And yeah, next will be about complex numbers, and don't worry, I won't cover the entire topic of complex numbers. If you want to do that, you can do that on your choice, but I'll just teach you the basics of complex numbers that are needed to calculate AC circuits. But anyway, thank you again for watching my video this week, and not really this week. I'm doing them so often because they are a great way to learn, and I recommend you to do that as well, because I need to learn them very well enough to explain to somebody else and explain it like why I did it and the steps and everything that I do for them. But yeah, okay, so remember, next video will be about complex numbers, and after that it will be more advanced AC circuits that will also require complex numbers in them. Alright, I will stop the video here and see you guys next video. Bye!